Hello, everyone. My name is Ryan Hartnett, and this is my final project for the Engineering 869 course, an Introduction to Robotics at San Francisco State University as part of the School of Engineering, which is offered by our instructor, Dr. Azadi, who does a great job and brings a lot of practical industry knowledge and research knowledge from academia to robotics. And what's cool about this course is that we look at a bunch of different platforms, like this SCARA robot here, or say a mechatronic tractor, or another robotic platform here, and start to think about how to design robots, how robots interact with the world, and then how to move the designs to get a desired path or trajectory. And so for our final project for this semester, we were to make a simulation of a SCARA robot. So a SCARA robot is, it stands for Selective Compliance Articulated Robotic Platform. And it has all these different joints where they move. And at each joint, it's powered by motors that are internal to this system. And then at the end, it has a worm drive that does it up and down Z motion. So you can imagine this robot moves in like a circle and can do a pick and place application, as you can see on this video on the right here. So now to introduce our final project, we were to make a robot that is in the industry. And part of this is understanding how to use Simscape. And I'll get into more details about what that is later, but basically it's like a physics modeling system that we can use and then apply robotics principles to control a robot in a simulation. And what's cool about that is it integrates with Simulink, and I'll also introduce that software a little bit later, but that software basically is a graphical interface to do some of these simulations and gives you an intuitive feel for how these systems work. And then in this final project, we were supposed to simulate an existing robot, use inverse kinematics, which gives us an idea, like we have a desired end effector here, which is this up and down. And from that, get the joint trajectories and positions to control a robot where we want it to go. And then we can also do the opposite, work from the base and understand where the forward kinematics of the robot is and control that end effector that way. And then we utilize in this project trapezoidal velocity profiles, which basically smooth the motion of the robot and makes it move, have a better response versus just doing a linear pathway or exactly. And then last, we use waypoints to move the robot around to the desired path or points that we wanted the end effector to end up at. So now I'll describe the software emulation. We're going to be using MATLAB, as well as Simulink, Simscape, and the Robotics Systems Toolbox. And I will switch to those three different pieces of software from Mathworks, and we'll get a look at what that is. So this is MATLAB. It stands for Matrix Laboratory. And what we can do is work from the command line and say, what's in my directory, make a directory, or, do simple mathematics like that, and it'll click through and show an answer for us. And this can go all the way up to differential equations, like, what it stands for is the Matrix Laboratory, so matrix, linear algebra, all that kind of stuff. And then you can also write an M file, which is like a script, and then I can run this script and it'll load all these values into the workspace. And I already kind of prepped this so that I could do this demonstration today. And then it shows you the folder of all the different items that are in the workspace. So now I will switch to the Simulink model that we made. And this is the Simulink model. Like I said, it's a graphical interface. So this is like doing like what the MATLAB is doing in the background, but instead it's using box functions that are passing arguments back and forth. So for this particular test, we developed a SCARA robot. And from this, you can see, so in this graphical way, we have this base here, and we populate the base with a world frame, its mechanical configuration, and then make adjustments with that. So if I double click, it expands that, and then you can see we have our base here, and then a world transformed to the base and things like that. And I'll go over this in more detail when I run the simulation. So last, I will show you what the Simscape puts out. And that's what this is here. So at the end of running that simulation, Simscape takes what we've put in Simulink and then puts it into the physical world in this simulation environment, and with the actual physical characteristics. So that Simulink is kind of like the scaffolding of the robot, and then Simscape implements the real world physics with that. All right, so let's get back to the presentation real briefly. And a lot of this work was done based on this great video by Dr. Muhammad Rzi Abbas in Pakistan. And if you are learning MATLAB and learning Robotics Toolbox, this is a great resource. And we use it as a companion for our course and for this project. So now I will go over the goals of the project. And that was to make this model that was simulated in a simulated version of the SCARA robot. And it had to follow these trajectories, go to these points and meet, we're going to make this design, build the model, and then have it follow this pathway. So I'm going to switch back to the Simscape model and kind of review what we did in Simulink, and then run the simulation for you. Okay, so again, back to the robot. This is, the graphical representation of this in Simulink. And then, so you have your base, which every robot has a base. And then the first joint is a revolute joint. So that's what these are. And then the next piece is a link. And then in each of these, there's a transformation that takes it from the end of the base to the link, and then from the link to the end of the link. And so that to the next joint. And so that's what we see out here. Again, these all contain those. So this would be link 2, and that connects to joint 3. And then joint 3 is that prismatic joint. So we have a revolute joint that rotates and a prismatic joint that just goes up and down and along an axis. And then at the end, our end effector is just, they call it a welded joint, and that's where that interacts with the environment and what we want. And we still have to do transforms to set it in place and relate how those things come together. And then what we're doing is we're creating this trapezoidal joint velocity profile. So in here, I actually like to run a script. So what I did was go back to MATLAB real quick. I ran this script. This reads in that robot, creates a rigid body tree, and then this loads the velocity profile that I want. And then that trapezoidal trajectory block here, this profile trajectory block, outputs a velocity, or its position, a velocity, and then a acceleration, but we weren't using that in our simulation today. And then we did an inverse kinematics. So we took in that the position command, and then this reads our rigid body tree, which is that robot that I showed you earlier, and then it outputs what the inverse kinematics position would be. So then that gets read into the robot, and so that is commanding the joints. So this Q1, Q2, Q3 is the revolute joint, and then the prismatic joint. And then this piece outputs the measurement, and then we do a forward kinematics. So we have all of those different things being read into that, and then that translates back out to an XYZ position for our end effector. And then we call that measured, and then we plot it in our scope here. So I'll show you this simulation, and what we end up having happen is this. So as you can see, it's following the joint trajectory that we wanted in a square pattern. And then I actually added, after it finishes its move, to come back to home. So that was something that I added a little bit extra. But you can see that it's also changing in the z-axis. So based on the values that I sent to it in that matrix of waypoints, it's changing its position based on that. So this will give you another run here, and yeah, gives you an idea. So the reason that this is working is that it takes about 5 minutes to run. So I did this ahead of time, so you didn't have to watch the computer do the calculation. But Simulink, using Simscape and the Robotics Toolbox, it is able to run that simulation. And I forgot to mention the Robotics Toolbox. It's a really handy toolbox. So all these functions that are in here came from the Robotics System Toolbox. So like this forward dynamics, you can get the Jacobian to map all the different joints and velocities. We have our inverse kinematics joint, box, and all those things. And that was actually developed by Peter Corke at the Queensland University of Technology. And then MATLAB started to integrate that into its Simulink software and the Robotics Toolbox. Okay, and that's pretty much an overview of the presentation. And I would like to say thank you to my classmates, Dr. Azadi, and the people I work with in the care lab at San Francisco State. I'm working on prosthetics and rehabilitation robotics. And yeah, just very excited to be here and share some of my knowledge, and happy to share my final project for this course. Thank you, and have a good day.